In the previous video, we have studied positive term series. And in a positive term series, the order of adding the terms did not matter. In the general case, where terms can be both positive and negative, then the order matters. So what can we do about it? That's what we are going to study in this video. Let's start. First, we classify series based on how it converges. That is, absolute convergence or conditional convergence. And here's the definition. We say this series, an from 0 to infinity, converges absolutely So what this means is that this series, so if we take the absolute value of each term and take the sum, if this converges, or if it has a sum, so this is a positive term series, right? So because each term here is absolute value, so it's a positive or maybe 0. So it's a positive term series, and if this has a sum, then we say the original series converges absolutely. On the other hand, if the series converges but not absolutely, we say it converges conditionally. So that means this has a sum, but does not converge absolutely. Okay, so that means if we take the sum of absolute value, this may diverge. So this diverges, okay? But if we don't take the absolute value, then this converges to some value, finite value. In that case, this series converges conditionally. Now, here's a theorem. That is, absolutely converging series has a unique sum, and the sum does not depend on the order of the sum. So let this series an be an absolutely converging series. Then we have 1. This series has a sum, so this converges. And 2, let an of k be an arbitrarily permuted sequence of an. Then we have this sum. So k from 0 to infinity, and the sum of this permuted sequence is the same as the sum of the original sequence. By the way, if you think this is trivial, let's go back to the definition of converging absolutely. So this says the sum of the absolute value of the terms has a sum. So if this is the case, then we say this series converges absolutely. But it doesn't actually say that this converges. Okay? So this is part of the theorem. Okay, so let's prove it. Okay, first of all, let's define two sequences, positive part and negative part. So define an plus that is equal to an if an is greater than or equal to 0, or 0 if an is negative. Okay, and another sequence an minus that is equal to 0 if an is greater than or equal to 0, or negative an when if an is negative. If we define this, then this an plus, this sequence, and an minus, this sequence, both are positive term sequence, positive term sequences. So that means this sum of an plus and sum of an minus are positive term series. And we should also note that for all n, that is non-negative integers, we have an plus is less than or equal to absolute value of an, and also an minus is less than or equal to the absolute value of an. So and by assumption, this the series an is absolutely converging. So this has a sum by assumption. That means we have a dominating series for this and this. So that is, this is a dominating sequence, series, is a dominating series of an plus and an minus. So, and since this is positive term series, this is a positive term series, and both are dominated by this. Therefore, this one, an plus, this series, and this one have sums. So they converge. This and this converge. They dominate monotone increasing and dominate bounded above, so they have sums. And therefore, this one, a 0, infinity, an plus minus an minus. This is, so by the linearity of series, we have this, an plus minus and sum of an minus. So this has a sum. However, this is equal to, however, However, an is equal to an plus minus an minus. So therefore, this left-hand side is equal to the original series, has a sum. So this converges. And we are done for part 1. And for part 2, this one is a positive term series, and this one is a positive term series. And so both sums do not depend on the order of addition. Therefore, this one, after all, does not depend on the order of addition. So the part 2 is done. So even if a series is not a positive term series, if it converges absolutely, then we are lucky to have its converging value. It has a sum, and the sum doesn't depend on the order of addition. So that's a nice property. On the other hand, if a series is conditionally converging, then there is a serious problem. So this is a theorem. I don't give a proof because it's too complicated. But anyway, this is a very interesting result. So let this series be a conditionally converging series. Then for any real number alpha, there exists a permuted sequence an of k of the original sequence such that the sum of this permuted sequence an of k is equal to alpha. You see, so this alpha can be any value. For any alpha, we can always find some permuted sequence such that this holds. So that means if we just shuffle the sum, the result can be any real number. This is a very strange result, but this can happen. So this is one of the strange things that can happen when infinity is involved. If this is a finite sum, then this can never happen because whatever order we add the terms, then the result is always the same. But when this series involves infinitely many terms, then very strange thing can happen. Next, let's study a few convergence criteria. So when we are given a series, it may not be always possible to explicitly calculate this sum, but we still want to know whether this converges or not. In that case, we may apply these criteria to check whether this does converge or not. The first one is called Koshys Criterion. So it's a theorem. Koshys Criterion. So let's see. Let this sum be a positive term series. And suppose the limit limit n going to infinity and nth root of an. So this an is always positive or 0, so we can always take this root. Converges to R. Okay, so if this limit exists, then first, if this limit R is less than 1, then the series converges. And 2, if the limit is greater than 1, then the series diverges. Okay, let's prove this. Okay, first one, suppose R is greater than 1. Then pick t, that is a real number, such that t is between R and 1. This is always possible because of the denseness of real numbers. Okay, and let epsilon be t minus r, which is positive. Okay, and since the limit of the nth root of an is r, there exists, so for this epsilon, there exists some natural number n such that for all natural number n, if this lowercase n is greater than equal to this uppercase n, then the difference between the nth root of an minus r, so between this is less than epsilon. I mean, this is the definition of the limit. So by definition of limit, we have this. Now, note that this n is finite, okay? Is finite. So that means for all lowercase n that is greater than this capital uppercase N, we have this. That means for infinitely many n, a natural number, we have this. Let's see. We have this inequality. So for this holds for infinitely many n's, right? And in particular, from this, we have n root of an minus r is less than epsilon. And from this, we have an less than r plus epsilon. But by the definition of epsilon, that is t minus r. So this is actually t. And if we take the nth power of both sides, we have an less than t to the power of n. And this holds for lowercase n greater than or equal to uppercase n, right? So if we take the sum from n from capital N to infinity, we have this. But this is less than or equal to n starts from 0 to infinity. But this sum, this is just a geometric series, so its sum is 1 over 1 minus t. Remember, this t is less than 1, so this does converge to this value. Therefore, this geometric series is a dominating series. Therefore, by the dominating convergence theorem, this sum converges. And we are done with part 1. And for part 2, if r is greater than 1, then that means nth root of an is greater than or equal to 1 for infinitely many n. So that means an does not converge to 0 because it's greater than 1. Therefore, we have studied the necessary condition for a series to converge, and that is the sequence comprising the series must converge to 0, but it's not satisfied here. Therefore, the series does not converge. And we are done. Let's see an example. Consider this series, and from 0 to infinity, an plus b over cn plus d, everything to the power of n. Okay, so we show that this converges if a is less than c. Okay, we are assuming this is a positive term series. Okay, and so let's apply Koshys criterion. So in that case, we take the limit of the nth root of this, an plus b cn plus d to the power of n. That is, so this is just an plus b over cn plus d, and this converges to a over c. So if a is less than c, then this is less than 1. Therefore, it converges. Otherwise, it diverges. And the next criterion is called D'Alembert's criterion. D'Alembert is this D apostrophe He's a Frenchman, so we pronounce it as D'Alembert criterion. Okay, let this an be a positive term series. And suppose the limit, in this case we take the ratio between two consecutive terms, an plus 1 over an, and this converges to r. So suppose this limit exists. Then 1. If r is less than 1, then the series converges. And 2, if R is greater than 1, then the series diverges. Now let's prove this. Okay, proof part 1. So suppose R is less than 1 and pick T between R and 1, and that's always possible. Then so because this limit exists and the limit is less than 1, then for an plus 1 and divided by an is less than t for all n greater than or equal to some sufficiently large n. Okay. That's due to the definition of the limit, right? Just like we did for the other criterion, Koshys Criterion. So anyway, so this holds for infinitely many n's that is greater than some capital N. Okay, so that means an plus 1 is less than, and maybe equal, less than or equal to tan. So we have an less than or equal to tan minus 1 less than or equal to t squared an minus 2, and so on. If we continue this, we get t to the power of n lowercase n minus uppercase n times a uppercase n. Okay, so if we take the sum then of this, then we have n from capital N to infinity t to the power of n minus n a n. Now this is, if we shift the index here and take this an out, we have n from 0 to infinity t to the power of n. And this is of course an times 1 over 1 minus t. So we have a dominating series that converges to this value. Okay, so therefore the series an converges. We say dominating convergence theorem. And part 2, suppose R is greater than 1. Then that means, so opposite of this one. So then that means an plus 1 is greater than an. Therefore, the limit of an is not 0. It's greater than 0. It's greater than 0. Therefore, the series does not converge. So diverges. And we are done. Okay, let's see an example. Consider this series n from 0 to infinity and some constant c to the power of n divided by n factorial, and c is positive. And this converges. And so to see this, let an be c to the power of n over n factorial. Then an plus 1 over an is this, n plus 1 factorial, c to the power of n factorial, and that is c over n plus 1, which converges to 0 as n goes to infinity. So this is, of course, 0 is less than 1, therefore this series converges. By the way, what happens if this limit, okay, this limit, an plus 1 over an is exactly equal to 1? Then what happens? Actually, according to D'Alembert's criterion, this case is useless, actually, because sometimes the series converges and sometimes it doesn't. For example, consider this series 1 over n squared. In this case, okay, so n plus 1, an plus 1 would be n plus 1 squared, and an would be n squared, and that is just n over n plus 1, everything squared. And this converges to 1. And this series actually converges. So this converges. And this ratio converges to 1. However, another series, 1 over n. In this case, it's 1 over n and 1 over n, so that's n over n plus 1. That converges to 1. But we know that this diverges. So when this is the case, we don't know anything from D'Alembert's criterion. And the same applies to Koshys criterion too. So nth root of the nth term converges to 1, exactly 1, then we don't know if the series converges or not. That depends. So that's all for this video. See you later. Bye.